I am your host. My name is Eric Geisels. I'm professor of finance at the Keenan Flagler Business School and a professor of economics at UNC Chapel Hill. I have the pleasure of introducing today's speaker, Shaohan Hu. Shaohan is the executive director, the executive director of the JPMorgan Chase Future Lab for Applied Research and Engineering, which has the beautiful acronym FLAIR. Prior to that, he was a research staff member at IBM, working on quantum computing with a focus on quantum circuits, algorithms, and applications. He obtained his PhD from University of Illinois Urbana-Champaign, where he worked. His work spanned topics such as AI, ML, IoT, mobile computing, and cloud computing. He's going to talk about a topic that is actually sort of a first, I think, for this, definitely a first for this webinar series. He's going to talk about quantum circuit optimization. A few things about housekeeping. During Shaohan's talk, please feel free to field your questions in the chat, which appears at the bottom of your screen. And then we will have some time for Q&A at the end of his presentation. Shaohan, it's a pleasure to have you. Thank you for accepting our invitation. I look forward to learning a lot from you about quantum circuits. Please go ahead.
All right, thank you, Eric, for the introduction. Let me share my screen. So as I was saying, I'm from the Future Lab for Applied Research and Engineering from JPMorgan Chase. So today I would like to talk about a couple of topics on quantum circuit optimization. A few recent works that I was involved in. Before we dive into the more technical content, I would like to take a minute to sort of promote our FLAIR organization under JPMorgan. So as Eric also touched upon, FLAIR stands for Future Lab for Applied Research and Engineering. We're a newly established organization under JPMorgan with the sole focus of carrying out applied research and engineering on the frontier new technology, including quantum technologies, AR, VR, IoT, and many more. So if you want to learn a bit more about FLAIR, please follow this URL or simply Google JPMorgan FLAIR. You'll likely find a link. And I would also like to mention that we are now actively hiring talents since this talk is on quantum. So if you have experiences in quantum computing or quantum communication and would be interested in our opportunity, please feel free to reach out to me. So, before joining JPMorgan, I was actually at IBM working on quantum as well, and now at JPMorgan, quantum is obviously also a very big focus of my day-to-day work. So my focus has been on quantum applications and software. I was involved in the building of the Qiskit quantum software package when I was at IBM rather. At JPMorgan, we're also working on a similar software package where we collect the different components that we use to build up quantum algorithms and build quantum applications. So in designing and building our quantum computing software package, we follow a very kind of modular principle in the sense to try to make all the different components modular and they can be used in a plug and play fashion. So then when someone, say, who wants to use the software package to implement certain quantum algorithms, it basically just involves piecing together all the different components provided by the underlying software. So my day in and day out job, has been, working with many of the components, trying to tune them, optimize them, things like that. And if you go down to the very bottom of things, all the different components are just different types of quantum circuits. So as you can imagine, quantum circuits are of the crucial importance, and they are the essence of designing and implementing quantum algorithms. So it makes sense to optimize quantum circuits, especially in the current NISQ era. NISQ stands for near intermediate scale quantum. So that means today's quantum devices, they're noisy, they're not error corrected. So if we want to take advantage of today's quantum devices, we better design our quantum algorithms and quantum circuits to make them not too long, not too complex. Because if you throw a extremely complex quantum circuit to today's NISQ device, by the end of the execution, the noise would have destroyed all the quantum information contained in the qubits. So quantum circuit optimization. To get a sense of why circuit optimization is important, I actually wanted to show a quick example to kind of give you an idea of why circuits that are unoptimized might produce undesirable results. So here I'm basically just preparing a very tiny toy example quantum circuit. So in particular, I'm preparing a Grover search quantum circuit that performs search to find the solutions to a simple three-set problem. So here, this DMAX format representation is the standard way of specifying a three-set problem. So in particular, it says we're dealing with 3 different variables spanning 5 different clauses. All the variables in a clause are ORed together, and all the different clauses are ANDed together, hence the conjunctive normal form for the 3-set representation. And I'm basically building a quantum circuit, representing this logical expression for the 3-set problem, and using Grover search to perform search, finding the solutions. So the QC here is the actual quantum circuit built. As you can see, it's a little bit too long to visualize nicely, in this single slide. So looking at the beginning and the end of the quantum circuit, you can see I used all 10 qubits of a particular hardware that I have access to. And the top 3 qubits are the variable qubits, corresponding to the 3 problem variables. All the rest of the qubits are sort of ancillary qubits. They help in holding intermediate values, and they will be destroyed at the end. And at the end, we're only measuring the top 3 variable qubits. So here are the execution results. So when I took the quantum circuit, I sent it to 2 different backends. One is a software simulator. The other is a actual quantum hardware. So as you can see, for each one of the backends, I had my execution done with 1,000 shots each. The darker bars represent the measurement counts for the simulator execution result. As you can see, the top 3 bars, top 3 darker bars, they actually correspond to the 3 different measurements that are circled. The circling here actually represent that they are the correct expected results to the original 3-set problem. So on the other hand, if we look at the hardware results, the lighter bars, actually the top lighter bars do not correspond to the correct result for the 3-set problem. So that's most likely due to the noise and sort of the NISQ nature of the hardware, where the quantum information had been destroyed by the end of the execution. So to take a little closer look at things to see where the problems might be. So here I'm looking at the compiled circuit right before the execution, to the different backends. As you can see, the compiled circuit for the simulator consists of about 1,200, quantum gates. whereas for the hardware execution, the quantum circuit, the compiled quantum circuit gate count is about doubling that. So there are many factors that can actually affect a quantum circuit complexity in terms of gate count, in terms of depth. There are two main, factors that we can be easily identified. One is the hardware characteristics. The other is the mathematical characteristics. So for hardware, there are many aspects of hardware that can affect the quantum circuit complexity. One very simple thing that we can imagine is, for example, the qubit topology on the particular hardware. If you have a hardware where the qubits are closely coupled, for example, to the extreme, if we have a qubit topology that's all-to-all connection, then it's very easy to implement quantum circuits on that because all the qubit pairs can interact with each other. If they're very loosely connected, then if you want to make two qubits talk to each other, then on the hardware, you might have to do a lot of swaps to bring them together for them to interact. That'll effectively increase the complexity of the quantum circuit. So that was the hardware characteristics. So in terms of mathematical characteristics, I'm more talking about the properties of the gate sets themselves. For different gate sets, they have different mathematical properties, which can enable different opportunities for optimizing the corresponding quantum circuits. So with that said, today in my talk, I want to be briefly discussing two most recent work that I was involved in, and each each touched upon one aspect that I just mentioned. So both the hardware and the mathematical properties. So for the first one, our goal was to target a 2D square lattice architecture and try to build an efficient multi-control Toffoli quantum circuit for this 2D square lattice architecture. This was worked on jointly with Marco Pistoia, Dmitry Maslov, and Jake Gambetta. A little bit kind of primer for people who are not entirely familiar with what multi-control Toffoli gates are. So multi-control Toffoli or MCT gates are an extension of Toffoli gates or the double control NOT gate, which has a nice visual representation here. So basically, it involves three qubits. The top two are control qubits. The bottom one is the target. So it basically says that the target qubit will be flipped if and only if both of the top two control qubits are in the one state. So I did a little kind of search through the Qiskit software repository. So it turns out that the Toffoli gate, the CCX CT NOT gate, is widely used in terms of implementing many different quantum techniques. For example, controlled RY gate, multi-control multi-target gate, Boolean logical circuits, HHL reciprocals. HHL is a quantum algorithm for solving linear system of linear equations. And in terms of building oracles for Grovers, for Bernstein-Vazirani, for Deutsch-Joseph, Simon's algorithms, which are the more kind of the tutorial type of quantum algorithms, and for algorithms like amplitude amplification, which is used in Grover search for folks who are familiar with that. So, what I wanted to say here is, the multi-control Toffoli gates are very widely used by a lot of other quantum computing techniques. So it makes sense to, for us to actually have a very optimized version of MCT available. So there exists, a lot of strategies for implementing multi-control MCT gates already. So the most prominent would probably be the textbook strategy from Nielsen and Tran, with a visualization shown here. So basically, it takes sort of a V-shape structure in terms of implementing the multi-control Toffoli circuit. So in this particular illustration, we're looking at five controls, V0 through V4. And the target qubit is this R qubit right here. So the A qubits are the ancillary qubits used for holding intermediate values. So basically for this V-shape, the left arm progressively computes the intermediate values and stores them in the ancillary qubits, where this bottom Toffoli gate computes the actual final value and stores it in the target qubit, and then the rest arm of the V-shape sort of uncomputes all the ancillary qubits, because of course we're talking about reversible computing. So the big problem with this sort of textbook V-shape implementation is that there's a huge linear dependency in terms of its implementation. So every single gate depends on the completion of all its previous gates. So with this linear dependency, it's impossible for us to say, parallelize the execution of the gates. And that leads to very deep circuits, which is not good for the current NISQ devices. So if you look at the other end of the spectrum, there are other strategies that exist for implementing MCT gates, but they involve even fewer or no ancillary qubits. So the good side, of course, is that they require a smaller number of qubits, but they produce even deeper circuits than just simple linear V-shape implementation strategy. So that goes against our desire to produce shallower circuits. So our goal for this work is to take the V-shape, the textbook V-shape implementation, and to try to optimize it for a 2D square lattice hardware architecture. In the sense that we can kind of get rid of this linear dependency and produce very shallow circuits in the end. So in trying to accomplish our goal, there are two techniques that we use along the way. One is called the H-tree topology. The other is called the relative phase Toffoli, as opposed to the traditional Toffoli that we briefly discussed before. So first, let's take a look at what H-tree topology is. So it's actually very simple structure, especially for the 2D square lattice kind of topology. So H-tree topology is essentially an efficient layout of balanced binary tree in a 2D square lattice. And so you can see there are a lot of H shapes that's embedded in this 2D square lattice, and it's this H kind of a fractal H shape rather, that can help us carry out divide and conquer implementations for our MCT on the 2D square lattice. Looking at a single H structure, then we can see there are multiple vertices sitting on this H structure. So for every single line segment, for example, the different edges within the H, we can imagine qubits sitting at the ends as well as at the middle point of the line segment. Then there are different situations in terms of qubit interactions. For example, if we look at this particular edge, ACF, for qubit A and qubit C, we can have efficient interaction between these two qubits easily, because they physically sit next to each other. But for the qubit pair A and F, we cannot have them efficiently talk to each other without swapping qubits around. So it gives us the idea of strategically placing qubits on the H shape in order to make the implementation very efficient. So there are different strategies that we can use in terms of placing qubits. As can be seen from a previous slide, the building blocks for building MCT circuits is the traditional Toffoli circuit. And it turns out there are different ways to implementing the traditional Toffoli circuits as well. Here on this page, I'm listing two different strategies. So this top one uses 6 CNOT gates. This bottom one uses 10 CNOT gates. But there's a crucial distinction between them that makes it such that it's beneficial for us to actually choose the bottom one rather than the top one, even though the top one uses a fewer number of 2-qubit CNOT gates. Because if you look closely, for this 6 CNOT implementation for Toffoli, actually it requires the interaction between all 3 pairs of qubit. It requires the interaction between the 2 controls. It requires between the target with both of the controls. So that doesn't really align with our observation that for H topology, some qubit pairs can have easier interaction, some cannot. So that's why we're choosing this bottom strategy for implementing MCT circuits using the H-tree topology, because even though it uses a slightly higher number of CNOT gates, it doesn't actually require the 2 control qubits to have direct interaction. So all interactions are between a control and a target. So to translate that into implementing on a H-tree topology, if we put the target qubit at the middle point and the 2 control at both of the endpoints, then we have efficient communication required, and we don't need to bring in swaps to make qubit interactions happen. So actually, it turns out we don't even need to use the true Toffoli gates to implement our MCT gates. We can use a sort of a simplified version of Toffoli gates, which is called relative phase Toffoli, because it turns out the phase information is actually not important in the implementation here. So here I'm listing 2 different implementations for relative phase Toffolis. The top one involves 2 qubits, involves 2 controls, and the bottom one actually is implementation for a 3-control relative phase Toffoli gates. So, and as you see momentarily, both will help us in terms of achieving very efficient implementation for MCT on the H-tree topology. So to sort of give a very simple visual representation of how we build MCT on H-tree topology. So here is a examples implementation strategy for a 4-control MCT on the H-tree topology, where the 4 C's correspond to the 4 controls, and the 2 A's are the 2 ancillary qubits used for holding intermediate value, and the center T represents the target qubit. So this is a complete kind of layout of how we can implement a 4-control MCT gate on the H-tree topology. So if we want to grow this 4-control MCT to say a 6-control MCT, we might think, okay, then we might need to grow this fractal structure of H-tree topology, for example, to the right, to bring in 2 controls and an ancillary qubit, and then a new target, turning the old target to a new ancillary, helping to compute the new target. But since we also had this 3-control relative phase Toffoli, we can essentially just add a control to either of the ancillary qubits, which currently only have 2 controls attached. So now they'll both be connected to 3 controls with the help of the 3-control relative phase Toffoli. So with that, we don't have to grow the H-tree topology, say, to the right. We can just opportunistically add more controls to available positions in our existing kind of old layout to achieve a new layout with a higher number of controls. So here are some results, from our investigation. For example, here are three example layouts for MCT implementations for different number of controls with 6, 9, and 12 controls. And it turns out, actually, with our proposed strategy, MCTs with up to 12 controls can be implemented with a minimum depth without any swaps, and the maximum level of parallelism can be utilized. So we also ran a set of experiments, sort of comparing our strategy to a baseline strategy, where the baseline strategy basically uses the V-shape implementation strategy, as mentioned in the textbook, and we have that kind of a logical quantum circuit mapped to a 5x5 grid using Qiskit's stochastic swap transpiler. And after that, that'll be used as the baseline quantum circuit. We also, of course, use our strategy to implement the quantum circuit at the same 5x5 to the square lattice structure, and then we compare the circuit depth between the two different strategies. As you can see, as the number of controls increases, our proposed method produces circuits that have very slow growth in terms of the circuit depth, because it can very effectively use the parallelism embedded in the H3 topology with the help of relative phase Toffoli gates. Whereas for the baseline method, it has a very dramatically fast increase in terms of quantum circuit as we increase the number of controls. So at the end of the day, to implement, for example, a 12 control multi-control Toffoli gate, our strategy will be producing a circuit that's a fraction, in terms of quantum circuit depth compared to the baseline strategy. So that was an example that I wanted to talk about of kind of taking advantage of the hardware characteristics in terms of designing a quantum circuit optimization strategy. Next, I would like to touch on the other aspect that I mentioned, which basically looks at the mathematical properties, characteristics of the particular quantum gate set that we're working with, and explore what are the optimization strategies that can be used to perform quantum circuit optimization. This was a joint work done with Dmitry Maslov, Sergey Bravy, and Ruslan Shidlin. Again, a little bit of a primer for Clifford Circuits. So basically, Clifford Circuits, when we talk about Clifford Circuits, we're talking about quantum circuits that involve a particular set of quantum gates. In this case, Clifford Circuits involves the Clifford Pauli XYZ gates, the Hadamard and the phase gates, and the CNOT gate. And sometimes you can see people also talk about the control Z gate, but that's equivalent to the CNOT gate. We can just sandwich the target qubit with Hadamard gates to produce the control Z gate. So Clifford group is a subgroup of all unitary transformations. And then, as it turns out, it plays a crucial role in many different fields. For example, quantum error correction, randomized benchmarking, quantum state isolation, et cetera, et cetera. So it's an important, set of quantum circuits that people, study very thoroughly. So as it turns out, people have been studying how to implement, how to synthesize optimal Clifford circuits. So as it turns out, it's again, prohibitively expensive. For example, currently there are only solutions for exact optimal synthesis for Clifford circuits up to 6 qubits. If you go above 6 qubits, then the current classical computing power is just not able to produce exact optimal synthesize within a reasonable amount of time. And the strategy that people use for exact optimal synthesize is basically exhaustive search. So our goal for this particular work here is to heuristically obtain the shortest possible circuit for any given Clifford unitary. So we already know that it's prohibitively expensive, so we do not strive for a exact optimal. That's why heuristic methods are used. So again, we use two techniques in kind of making up our proposed solutions. So one is Clifford specific template matching. The other is symbolic peephole optimization. So let's look at template matching technique first. Technique matching is actually widely used technique that people have been using for optimizing quantum circuits. So it involves the following steps. So first, we identify a template. What is a template? A template is basically just a sequence of quantum gates that actually compute the identity. So in this case, let's say we have a template T, which consists of m different quantum gates, and this sequence together, they compute the identity. So if, say, we want to optimize some target quantum circuit C, which is very much complex, involves many gates. If we can search through this target quantum circuit and find, say, a match for a subcircuit, from this template. For example, in this case, for this M circuits in the template, if we're able to find a match, from the target circuit matching P of the circuits from the template, then we are able to replace these P circuits with the M minus P circuits, I minus P gates, and then potentially be able to say reduce the cost, reduce the complexity of this target circuit. So this might seem a little abstract, so I prepared a little animation that hopefully will make the point very easy to see. So here you can see we have a template consisting of 5 quantum gates, sorry. And this 5 quantum gates together, they compute the identity. And say at the bottom, we have a long quantum circuit that we want to optimize. First, we find that, okay, we're able to find a match of this substructure of 3 gates within this template. We can find a match in the quantum circuit. And then it turns out with, we're able to commute the 3 matched gates within the quantum circuit to make them all sit next to each other. Then if that's possible, we're able to replace the matched substructure and with the rest of the template. And a tiny detail here is that we need to be using the conjugate, the inverse of those gates from the template. So after this substitution, then we essentially, in this toy example, reduced the gate count for the target circuit by 1. And so that was a very kind of cartoonish illustration of how template matching works in a nutshell. If you look at the details of template matching, it's very obvious that matching can actually be done in both directions. For the little illustration, it was done from left to right, but you can scan the quantum circuit from right to left as well, obviously. And when preparing the set of templates used for performing this template matching tasks, we want to also make sure that all the templates are independent from each other, because otherwise you might run into infinite loops where templates are matched, in a kind of interleaving fashion, non-ending fashion, which we want to avoid. So for the illustration, we can see we find the match, we do the substitution, and we shrink the target circuit by 1 in terms of gate count, and that is conditioned on the fact that we are able to move the matched gates together, through commuting with their neighboring gates. If we're not able to do that, if they do not commute, then the substitution cannot proceed for obvious reasons. And if we are able to do the substitution, then we only want to carry out the substitution when it's beneficial. And beneficial, what beneficial means depends on your particular scenario. For example, do you want to reduce a certain type of quantum gates? And quantum gates have a different, implementation cost. For example, hardware implementation cost for different hardware. So, that also need to be taken into consideration. And this whole template matching, steps, they are normally carried out in a iterative fashion. They're done, over and over again until some convergence criterion is met. For example, if you've done the template matching iterations once, and there's no modification done to the quantum circuit whatsoever, then that might indicate that you've reached the convergence. So that's sort of the what the traditional template matching techniques, how it's used to perform quantum circuit optimization. Specifically for Clifford circuits, we have a few other points that we introduced in template matching to perform optimization for Clifford circuits. So first, since we are working with a very particular set of quantum gates, we can first partition our target quantum circuit into different stages. In our case, we call it compute, poly, and swap. So basically, given a quantum circuit, we want to first push to one side all the swap gates, and then push to another stage all the poly gates. Then we're left with these 3 different stages, where obviously poly stage contains a layer of poly XYZ gates, swap, so of course just swap gates, and for compute, we have a partition of the we have a section of the circuit that consists of only hardware gates, phase gate, and C0 and control Z gate. In terms of pushing the poly gates, through the rest of the gates, it can actually be done, very easily following simple rules. For example, if you want to push a poly X gate through a hardware gate, it becomes a poly Z gate. If you want to push it through a phase gate, it becomes a Y gate, so on and so forth. So after this partitioning is done with a given circuit, we then can go ahead, carry out our iterative optimization, template matching optimization on the compute part of the quantum circuit. Upon the convergence, we can then use some simple heuristics to optimize the swap section of the quantum circuit. Obviously, we don't need to do anything to the poly section of the quantum circuit because it's just a single layer of poly gates. So that was the template matching, strategy that's kind of tuned specifically for Clifford circuits. That's the one part of the solution that we proposed in terms of optimizing Clifford circuits. The other part of the strategy is to use a technique called a peephole optimization. So for folks who are not familiar with what peephole optimization is about, it's also a iterative optimization. In this case, a iterative local optimization technique, which basically at each iteration chooses a subcircuit spanning a very small subset of qubits. And then it replace this chosen substructure with a optimized version drawn from a pre-computed database. Say you have a circuit that's involves 15 different qubits. Then say at each stage, at each iteration of peephole optimization, you pick say 2 qubit in particular and look at a particular substructure within those 2 qubit gate sequences and replace those substructure with a optimized version that's pre-computed and stored in the database. There are obvious restrictions and limitations to the traditional peephole optimizations because it's limited to very few qubit substructures, and such substructures must be completely decoupled from the remaining qubits, because otherwise you cannot go ahead with substitution. So in order to overcome this limitation of the original peephole optimization, we had proposed this technique called the symbolic peephole optimization, for which we basically introduce this set of what we call symbolic polygates to help us decouple the selected peephole subset from the rest of the circuit in a way that we are able to proceed with the substitution of the selected substructure. So again, I'm hoping to use kind of a small example to illustrate what a symbolic peephole optimization process looks like on a very tiny kind of toy example. So here we have this toy example where say A is our selected subset and B is represent the rest of the quantum circuit. So first, we identify all the C0 gates bridging A and B. In this case, we have 2 different occurrences of C0s connecting E and B. For both of them, we replace those 2 qubit C0, the original 2 qubit C0 gate with a symbolic poly X gate, here represented as an X, with a label. So after this, substitution using the symbolic polygates, we completely separated A and B. That means at this stage we can proceed optimizing A using the original peephole optimization without any restrictions because it's decoupled. So with simple kind of commuting rules, we're able to push the symbolic polygates actually to one side, to the end in this case, to the A substructure. And once we're able to do that, we can then lift this symbolic substructure, symbolic polygate, embedded substructure back to the full circuit by replacing the symbolic, replacing the introduced symbolic polygates back to the original gates. In this case, we're left with a single symbolic poly X gate, so that becomes a C0 gate connecting E and B. And here, in the pushing of the symbolic polygates, we introduce the phase value that needs to be taken care of by adding another phase gate as well. So that was kind of a toy illustration of how symbolic peephole optimization proceeds in terms of optimizing, Clifford circuits. Basically, introducing the symbolic polygates, carry out sort of the original peephole optimization, and then lift the circuit back to the full, lift the subcircuit back to the full circuit status. So now putting everything together, we have discussed the template matching technique and the symbolic peephole optimization technique. So combining them both, we have our final full solution for optimizing Clifford circuits. So basically, given a circuit, we partition the circuit into three stages. We then run multiple passes of template matching and swap optimization until the circuit reach a convergence stage. After that, we then carry out symbolic peephole optimization to further reduce the number of 2-qubit gates. Upon the completion of which, we then have another set of passes of template matching on the resulting quantum circuit to further reduce single qubit gate count. So that's sort of a sketch of the full proposed solution using both Clifford template matching and the symbolic peephole optimization. To sort of demonstrate the performance of our proposed solutions, we carried out 2 sets of experiments. So for experiment number 1, we basically want to run our method on circuits that contain a low number of qubits, for which we already have the optimal solution. So basically, the 6-qubit Clifford circuits. We want to run our method on 6-qubit Clifford circuits to see how well our method can recover the quantum circuits in terms of reaching the optimal number of CNOT count. So that was kind of the low qubit count optimal solution comparison experiment. Then we want to also experiment with quantum circuits that have much higher number of qubit count and see how well our proposed method performs on those much more complex quantum circuits. So for the 6-qubit Cliffords, we randomly generated about 1,000 Clifford unitaries with a number of CNOTs ranging from 5 to 15, because you cannot go below 5, otherwise there will be qubits that are kind of decoupled from the rest of the qubit, in the first place. So we have CNOT counts from 5 to 15. For each unitary, it's randomly resynthesized and then optimized using our technique. And then we are able to compare the resulting circuit CNOT count from the optimal value looked up from a pre-computed database. As you can see, with the higher amount of time allowed for the optimization to carry on, we're able to recover more and more circuits in terms of reaching optimal CNOT counts. We pay attention to CNOT because obviously the 2-qubit CNOT gate is the most expensive of all the quantum gates considered in our problem scenario. So essentially for 10 to the 4 seconds, we can see we're achieving close to 80% in terms of recovery of optimal CNOT count. And in the end, we are able to recover 98.9% of circuits in terms of reaching optimal CNOT count. And for the worst case, we're also within 1 CNOT count from the optimal version of the circuit. So that was the low qubit count experiment comparison to the optimal solutions. For this next set of experiments, we wanted to experiment on quantum circuits that involve a much larger number of qubits. So the particular experiments that we selected is a Hamiltonian evolution by cluster state, for which we selected different topologies with varying number of qubits, basically ranging from 4 or 5 qubits, ranging from 5 qubits to about 50 qubits. And also the transformation, for the different transformation, we tuned the layer count from 1 to the transformation period. And we, for the experiments, we want to study, okay, we run our proposed optimization solution and compare that to a simple greedy, synthesizer, and see how much our proposed solution can overperform the simple greedy synthesizer. So the solution, the result is shown in this figure. As you can see, as the number of qubits increases, the performance advantage of our proposed solution kind of over the simple synthesizer dips a little bit. That's because we restrict our experiments within a confined time limit. So with higher number of qubits, our solution will not be able to have as many iterations to optimize the circuits as it would want it. That results in a little dip in terms of performance. But still, you can see, in general, we're achieving anywhere from 15 to about 50% in terms of performance increase over the simple heuristic greedy synthesizer in terms of optimizing the quantum circuit and reducing the CNOT count in the optimized version of the quantum circuit. So I believe that's actually the last slide of my presentation. I understand that this is probably a little different from the application of quantum computing on the finance problems, which honestly is also another focus of what we do at JPMorgan Flare. But I want to talk about this topic with the intention to kind of introduce this whole problem or this sense of optimizing quantum circuits to the audience with maybe a couple of take-home messages at least. So first is that quantum circuits complexities, they can be affected by both hardware characteristics and the gate set mathematical properties, as the two pieces of work that I've discussed have illustrated. And obviously, quantum circuit is very important, at least in my opinion. It can bring substantial benefits, especially in the current NISQ era. So it's good that when we try to devise our quantum solutions for the problems that we're trying to solve, that we be mindful of optimizing quantum circuits before sending it down to different backends for execution. So that'll be my presentation. I'll be glad to take any questions if you have any.
Thank you. Thank you, Shaohan. That was a wonderful presentation. There's one question in the chat, but before we come to that, I'd like to perhaps pick on the last things you said. I mean, if you think about financial applications, perhaps would it be amplitude estimation where you kind of run into CNOT gates quite a bit, where you would see the, I mean, you kind of say that the benefits are depending on the application or the context. I mean, if you were to compute option pricing models, or I mean, that's one of the three prime financial applications. Is that where you're thinking to get most of your circuit optimization sort of advantages in financial applications, or would it be, Monte Carlo? I don't think it would be Monte Carlo simulation, but anyway, but what's your thought on that? What would be your bet in terms of where this will have the biggest impact in financial, in fintech?
Yeah, in fintech, again, that's a very, complex, question, because, we're still in NISQ era, and
yeah, sure.
we don't have hardware devices that are, say, capable of outperforming any of our classical solutions today.
No, I was more thinking about if you had to design your circuit on comparing different options on the current quantum computing platforms. Yeah. That's sort of, I don't want to get into the comparisons.
Sure, yeah, I think, an amplitude estimation, that's, certainly that actually is another topic that I'm currently working on as well. which has applications in various different derivative pricing, as you also mentioned. And we experiment with that on different hardware backends. For example, on the superconducting qubits, architecture, as well as on trapped iron, for which I want to say I personally have seen performance difference between those two different architectures. Partly due to for example, the qubit connectivity, which would affect the final circuit's complexity, because for trapped iron you probably have a all-to-all connectivity. For a superconducting qubit, it's a little less connectivity compared to its counterpart. So that's certainly something that we want to pay attention to in terms of running that.
There's one question in the chat. I assume you may have access to it, the chat as well, but it's regarding slide 38. So maybe you want to share your screen again if you want to. So it's about to kind of give a little bit more explanation on that sequencing of are these templates or matched gates the ABCD example that you illustrated. I think it's slide 38. If you want to reshare your slides.
All right. So
this is by Abhijit Rao.
Can you guys see my?
Yes, we can.
Okay. What was the question again? Sorry.
Oh, I'll read it again. So it's on slide 38. Can you please dwell on the A, B, C, D, H, etc.? Are those the templates or matched gates?
Oh, sure. Yeah. So here are the set of templates that we identified for our experiment for the optimization of Clifford circuits. Mm-hmm. So if you actually look at every single one of them in detail, you will find that they all compute the identity. So in terms of optimizing a quantum circuit using these templates, for example, if you are able to match a quantum circuit, let's pick H in particular, and say if you're using this particular template to match a quantum circuit, if you're able to match, say, up to this portion of the template, then you can take this part out from your target circuit and then replace it with the inverse of this part. Mm-hmm. So essentially, by just looking at it, it involves, a decrease in terms of the gate count. So yes, that's this is the set of templates, and they are, particularly chosen for optimizing Clifford circuits for this piece of work.
Thank you.
Yeah.
I think we're sort of really almost out of time. Again, Shaohan, thank you so much for presenting this work. I actually learned a lot. I haven't listened too much to circuit designs, and this was very useful. To all of you, thanks for participating today. This was recorded and will be posted on YouTube. For all future quantum computing webinar in FinTech, which are co-hosted by the Keene Institute and the NC State IBM Q-Hub. Stay tuned, visit our webpage, and I really want to thank all of you, and stay tuned. Thank you very much. Take care.